the confidence intervals for population proportions. The point estimate for population proportion, which is the population proportion of successes or the number of yes, is given by the proportion of successes in a sample and is denoted by p hat, which is x divided by n. X is the number of successes in the sample, and n is the sample size. The point estimate for population proportion of failures is q hat, which is denoted by 1 minus p hat. The symbols p hat, q hat, as you can see, are read as p hat and q hat. So when you have a population, you want to estimate the population proportion, or for example, since we are getting closer to election, the proportion of people who vote for Trump. What are you going to do? Are you going to ask everybody in the United States who are eligible to vote? Of course not. You're going to take a random sample and ask them, are you going to vote Trump? Yes or no? The number of people who say yes is basically your successes on the numerator. And n is the number of people that you ask, are you going to vote to Trump, yes or no? So that's how you calculate the point estimate for proportion. Then the question is that proportion a true proportion for population or not? Well, there are a lot of factors involved. Which state, which city you're going to collect data. Success means the number of people who said yes, successful surgeries. So in different contexts, in different questions, it has different meaning when it comes to success. For example, if you're counting the number of green M&Ms in a big jar, the green M&Ms count as the success. If it's not green, then you say that it's a failure because it's not green. Or if you're collecting data about people who drink coffee every day, if you ask people, okay, do you drink coffee every day? Success is those people who basically drink coffee. The rest of the people who say, no, I don't drink coffee, or I only drink tea, or any other beverages, it counts as failure. Very good. An interval estimate is an interval or range of values used to estimate a population parameter. Perfect. We know that if we take a sample and calculate the proportion for that sample, it might not capture the true population proportion. So that's why you're going to use an interval or range of values to feel a little bit more comfortable about capturing the true population parameter, in this case, population proportion. So what are the steps? First, we need to find the level of confidence, C, which is the probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a large number of times. Okay, what's next? In the next step, we need to find the critical value. For a proportion, the critical value is basically Z sub C. Remember the definition of critical value. The level of confidence C is the area under the standard normal curve between the critical values, negative ZC and positive ZC. Critical values are values that separate sample statistics that are probable from the unusual or improbable ones. Again, this blue area is your confidence level. 100% minus C divided by 2 is the area to the left to the right. That's why we divide it by 2. 1 minus C, 1 is 100%. This is the total area, which is 100%, minus C divided by 2 is the area to the left, the area to the right. For example, if you have 90% level of confidence, 10% divided up into two proportions, which is 5% to the left, 5% to the right. The critical value, or ZC, on the left is negative 1.645, on the right is 1.645. Again, some popular level of confidence are 90%, 95%, 99%. But again, in the context of the project, you need to investigate what is the level of confidence. If you are not sure about that, you need to ask the domain expert. If it's not given, it's safe to assume that it is 95%. So for 90%, the critical value is 1.645, 95%, 1.96, 99%, 2.575. Then you need to find the margin of error. Remember the definition. Given a level of confidence, the margin of error E, sometimes called maximum error of estimate or error tolerance, is the greatest possible distance between the point estimate and the value of parameter it is estimating. Now, for confidence interval for population proportion P, the margin of error is ZC times square root of P hat, Q hat, divided by N. Then P, or population proportion, is bounded between P hat minus E and P hat plus E. The probability that the confidence interval contains P is C, assuming that the estimation process is repeated a large number of times. Q hat is P hat opposite, or 100% minus P hat. So Q hat is the probability of failure. P hat is the probability of success, and Q hat is the probability of failure. Very good. Excellent. Any question before we move on to the next slide? So here we have a survey of 1,000 US teens, probably very old data. 372 said that they own smartphones. Find the point estimate for population proportion of all US teens who own smartphones. So for now, we're just going to go over the formulas. Then we're going to jump into Jupyter Notebook and do the calculation using our codes. First of all, N, the sample size is 1,000. X, the number of people who said yes or successes is 372. Very good. So now we can form P hat, calculate the sample proportion, which is X divided by N, 372 divided by 1,000, which is 0.372 or 37.2%. Okay. So the point estimate for population proportion of US teens who own smartphones is 37.2%. But is this a true population proportion? It means that we need to take more samples or use statistical analysis techniques to construct a confidence interval. Question says construct a 95% confidence interval for population proportion of US teens who own smartphones. Let us begin. You know p hat is equal to 0.372, q hat, which is 1 minus 0.372 or 0.628 or 62.8% is the probability of failure for people who say no. N is 1,000. First of all, you can verify that if it satisfies normality. N times p hat is 1,000 times 0.372 or 372, which is more than 5, and also n times q hat, which is 1,000 times 0.628, which is 628, which is more than 5. So the normality is met. Using ZC, which is 1.96, the margin of error is equal to ZC times square root of p hat, q hat divided by n. So the margin of error is equal to 1.96 times square root of p hat, which is 0.372, q hat 0.628 divided by 1,000. Well, if we do the calculation, it is 0.03. So this is the distance between the true population proportion and the sample proportion, about 3%. So this is just the distance, the margin of error. Now we can go to the next step and find the lower bound and upper bound for our confidence interval. These are the criteria for normality. Some books use 5, some other books or authors use 10. So they're basically saying that, hey, since we don't know anything about normality, and we want to use ZC, remember that, to use Z, you have to have a normal distribution. So they just multiply n and p hat, n and q hat, as long as these two numbers are more than 5 or 10. Again, some books use 5, some other books, they are on the safer side, they use 10 to make sure the normality is met. So now that you have the margin of error, you can jump into calculation for your left endpoint and the right endpoint. For the left endpoint, you have p hat minus e. For the right endpoint, you have p hat plus e. The left endpoint, 37.2% minus 3%. Right endpoint, 37.2% plus 3%. After doing the calculation, we can say that, hey, we are 95% confident that the proportion of US teens who own smartphone is in between 34.2% and 40.2%. Again, this data are probably very old because the percentage that they show, well, it might not capture the true population proportion. Nowadays, everybody's using smartphones. That is for the sake of calculations and feeling comfortable about the basics in calculating the lower bound and upper bound for a confidence interval. Let me run the poll. So let's jump into Jupyter Notebook and run the code. First of all, import NumPy as NP. From scipy.stats, import norm everybody. Set n to be 1,000 and x to be 372 with confidence level to be 95%. Guys, again, these variables are not fixed. You can rename them as well. Let me paste the code in the chat for you. So you have all the information here. Okay, everybody, please be on your Jupyter Notebook or Google Colab. Either is fine. Let us calculate p hat. P hat is defined as x over n. We have to do a little bit of calculation here. We need to form the fraction x divided by n. The formula for standard error, we're going to use square root. So np dot square root, which is p hat, times 1 minus p hat. This is basically your q hat, everyone. Divided by n. Here we go. Z value, as you remember, is norm dot ppf. This function basically takes the area and calculate the z-score for you. Norm dot ppf, 1 plus confidence level divided by 2. And the margin of error, as you remember, is the critical value times the standard error. Let me paste the code in the chat for you so you have access to everything. Now, do the calculation. The confidence interval has a lower bound, p hat minus the margin of error, and p hat plus the margin of error. I want you to run these codes and write your final answer in the chat for me, everybody. Very good. Thank you, everyone. Nice work. So what if you change the confidence level to 99%? What happens to the confidence interval itself? It becomes wider. If you change it to a different confidence level, you see changes in your confidence interval as well. So 90%, 99%. But basically, let's go back to 95%. What if I change in the sample size? if you have more values in your sample size, as you can see, there is a huge change in your confidence interval. So let's just go back here. Think about the following question. The figure at right from a survey of 498 US adults is given to you. So they had a survey of 498 US adults. 71% think teenagers are more dangerous drivers. 25% of 498 people think that people over 65 are more dangerous drivers. And out of 498 people, 4% has no opinion. You would like to construct a confidence interval, 99% confidence interval for population proportion of US adults who think that teenagers are more dangerous drivers. What is the very first step? Note that here, p hat is already given to you. P hat is 71%. But what if I ask you to find X? How many people said yes? Remember that P hat is equal to X divided by N. You know N is equal to 498. You have your P hat. So what is X? X is N times P hat. Do a little bit of algebra, everybody. 498 times 71%. What is that number, everyone? What is X? If I do the multiplication, how many people said yes? So it's going back to algebra. Okay, you can round it up to 354. If you do the multiplication, 354 people said, yeah, we think teenagers are more dangerous drivers. Okay. Q hat, which is 1 minus P hat, is about 29%. Now, if I ask you to calculate the margin of error, it is going to be ZC times square root of P hat, Q hat divided by N. ZC for 99% confidence level is 2.575. So if you do the multiplication, it is 2.575 times square root of P hat, Q hat divided by 498, which is about 5%. Okay, let's find the left endpoint, which is 71%, minus 5%, and right endpoint, which is 71% plus 5%. So the population mean of US adults who think teenagers are more dangerous drivers is in between 65.8% and 76.2%. Again, we are not 100% confident about the true population proportion, but we are 99% confident about that. With 99% confidence, you can say that the population proportion of US adults who think that teenagers are the more dangerous drivers is in between 65.8% and 76.2%. Now, what is the Python code that you're going to run? Your practice, everybody. Take your time, write the code for me, type it in the chat. Then we're going to look at it together. So you can just copy and paste from the previous code that you have and just make some adjustments. Given data, you have n, which is 498, and we calculated x, which is 354. The level of confidence, 99%. We calculate the p hat. And then the q hat is 1 minus p hat. And let's see, we have the z value, which is norm dot ppf, the area divided by 2, and then the margin of error. Now let's just change this, 99% confidence interval for population proportion of US adults who think teenagers are more dangerous drivers. So let's run the code. And as you can see, you get, 65.9% to 76.32%. Very good. Beautiful. Nice work, everybody. Good job on your code. So remember that here we did a little bit of algebra to calculate x, so we can plug that into our calculation. In this question, you had 71%. P hat was already given to you. P hat is 71%. To calculate x, we just multiply n and p hat. N is 498 and p hat is 71%. If you do the calculation, you get about 354 who said yes. Very good. Good job, everyone. Nice work. Now the question is, how do you measure? How do you know how many data, how many people you need to include in your survey? Finding a minimum sample size to estimate P. Suppose you have C confidence level and a margin of error E. The minimum sample size N needed to estimate the population proportion P is P hat times Q hat times ZC divided by E to the second power. Just an important piece of information. If there is no information about P hat and Q hat, then you have to use common sense, 50%, 50%. For example, if you're interested in knowing or collecting information about how many people, what's the proportion of people who vote Trump or Biden or any other person, common sense says 50% might vote to the candidate and 50% might not. So if you don't have preliminary information or estimation about P hat, Q hat, you're going to use common sense 50%. In this example, you are running a political campaign and wish to estimate with 95% confidence the population proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3% of population proportion. Question says, well, find the minimum sample size needed when no preliminary estimate is available. So, for example, you're interested in knowing who's going to vote Trump or Biden or any other person. You want to be 95% confident about that. What are you going to do? How many people are you going to ask? This is basically the question. Well, let's go back to our formula. because we don't have any preliminary estimate of p hat is 50%, q hat is 50%. Since it says 95% confidence, critical value is 1.96 with margin of error 3%, because it says it must be accurate within 3% of population proportion. Now solve for n. We have a nice formula. N is equal to p hat times q hat zc divided by e to the second power, which is 50% times 50%, 1.96 divided by 3% to the second power, which is about 1,067.11, or if you round it up, you need to ask at least 1,068 people. Right? So it's important to make sure how many people you need to ask, or in general, how many data needs to be in your sample to have a good accuracy, everybody. So as a data scientist, we need to feel comfortable about these. How many data needs to be included in our collection?